Good evening, guys.
Good evening. Good evening, sir.
Yes. So we'll get started with the next topic. 1 minute. So we'll get started with the last topic of this chapter, which is Earth's magnetism and the elements of Earth's magnetism. So basically, you would have seen a compass, right?
Yes.
So 1 minute. So if you see a compass, right, then how is that compass? Why is my screen share not coming? Yeah. So the question is, how is the compass able to show deflection? So basically, what is a compass needle made up of? It is also a small magnet, right? It's a magnetic needle. And we know that a magnet will start revolving only in the presence of another external magnetic field. So if you take a compass, right, and just hold it in your hand like this, then you can see that the needle will start getting deflected, correct?
Yes.
So where is that magnetism coming from? It is because of the natural magnetism that is exhibited by the Earth itself, which is called as Earth's magnetism, or some books refer to it as terrestrial magnetism. Now comes an important question of how is Earth able to show magnetism? Because I told you there is only one law or one basic rule where magnetism can be exhibited. It is when the charges are in motion, right? Means I need to give an explanation saying that around Earth there are charges and those charges are in motion, due to which it is able to exhibit magnetism. But if you see the real fact, nobody is clear of why it is able to exhibit. There are few theories, and some of the theories are nearly close to what we can say, yes, this would have been the reason. Okay. So the first one is called as the dynamo effect. So dynamo effect mainly says that if you take the layers of Earth, right, the outer core of the Earth, right, has molten iron, in the sense the iron is in the liquid form and other heavy elements in the liquid form. Now what will happen? So this is about the outer core, and the inner core, what happens is solidifies under the influence of gravity. So what will happen is these metallic fluids are there, right? If the metallic fluids which are there in the outer core of the Earth will cause electric current, and due to that current, there is magnetism generated. That is one of the theories that is proposed. So what is happening in the outer core? You have molten iron and other heavy elements in the liquid form. The inner core, what you have, it is solidified. So then the motion of the metallic fluids which is taking place in the outer core will give rise to electric current, and that will in turn give rise to magnetic field or field lines, is what one of the theories proposes. And the second one is about ionization of the outer layers. So ionization means what? Ions are getting created. When they say ions, they are charges. So this theory, what it tells us is that the rotation of Earth, we know that Earth revolves about its own axis. So when Earth is revolving about its own axis, the theory says there is a strong electric current that is produced due to the ionization of the outer layers of the Earth. And when this happens, they are saying that the movement of charges takes place, as a result of which magnetism is induced in the Earth. Right? But if you see, if this kind of ionization can happen because of the rotation of Earth and you're able to see some magnetism, right? Then the magnetism would have been very, very, very weak. Okay. Now, if you see, you can measure the magnetism, which will be in terms of few Gauss. Earth's magnetism will be generally in terms of few Gauss. So out of these two theories, if you observe, right, the dynamo effect has given a more valid explanation for the amount of magnetic field that we are able to sense. That is why dynamo effect is more acceptable theory, but that is not the exact theory of why Earth is exhibiting magnetism. So that is the first point that we need to note. So to conclude the whole story, nobody will ask you the reason of why Earth is exhibiting magnetism. No question will come.
Sir,
Tell me.
so I'm not able to follow the second part. Can you repeat that? That being magnetism being induced due to the ionization of the outer layers of Earth. I'm not able to catch that line.
So if this is the Earth, outer layer of Earth, what will happen is there are certain layers, right? There will
Yes,
be
sir.
some wind and all other things. So due to the rotation of Earth, what will happen is the wind particles are there, right? They will get ionized is what they are saying. And that ionized charge particles, when they are set into rotation, will have some electric current. And that electric current would induce magnetism is what this theory says.
Okay, sir.
Okay, yeah. See, some books speak about the solar wind also. So as I told you, nothing is clear.
Okay.
So that is not our headache also as of now. We are only concerned about how magnetism is measured at every point on the surface of Earth. That is what we are concerned about. What that value is, how will a compass respond to that value? As an end user, we are concerned about it. Okay. So if you take Earth, okay, let me show you 1 minute. Let me show you a simulation. One minute. I missed it somewhere. Okay. Anyways, we'll come back to the theory itself. So if you take this Earth, right? So with respect to Earth, there are two important points that we need to make a note of. So we know that Earth is going to be spherical in shape. Then when you draw an imaginary line like this, we call this as the axis around which the Earth is revolving. Then for this Earth, if I call this as north and this as south, then this can be called as geographic north, and this is called as geographic south. Is that clear?
Yes, sir.
Right. So if you are able to draw, listen to this very carefully. Okay. If you are able to draw an imaginary line passing through the geographic north and the geographic south, you call it as geographic axis. So what axis is this? This is the geographic axis. In a similar way, across the same earth, instead of drawing an axis, if you are able to draw a plane, if you are able to cut through a plane, then that is called as geographic meridian. Okay. So if you are able to draw a plane which is perpendicular to the axis and passing through the north and the south pole, you call it as meridian. And what meridian is this? It's called geographic meridian. So what I'm trying to tell you here is axis is a line and meridian is a plane. Is this point clear?
Yes, sir.
Yes, sir.
Right. In a similar way, what will happen is Earth is exhibiting magnetism. No, if you actually try to keep the compass, you know how to draw the magnetic field lines, right? Using a compass. So in whichever direction the north pole of the compass is going to show will give you the direction of magnetic field. Now, if you try to draw the magnetic field lines around the Earth, if this is the north pole and wait, let me change the color. If this is the north pole and this is the south pole, then you can observe that the magnetic field lines will start from the geographic south and go to the geographic north. Listen to this very carefully, okay? So the magnetic field lines, where do they start from? They start from the geographic south and go towards the geographic north. Okay. So what I'm trying to say is the geographic north will coincide with the magnetic south and the vice versa. This is a very, very, very important point that we need to note. Am I clear with what I mentioned?
Yes,
The
sir.
magnetic north coincides with geographic south and the vice versa. So this is one more important point you need to make a note of. Okay. Now, if I am saying that the magnet is going to exist something like this, this is south, I'm sorry. This is north and this is south. I'll call this as magnetic south and magnetic north and magnetic south. Then if I try to draw an axis through the magnetic north and the magnetic south, then this axis is called as magnetic axis. Guys, we discussed about two axes. Listen to this carefully. One is called a geographic axis and the other is called as magnetic axis. So geographic axis is an imaginary line that passes through the geographic north pole and the geographic south pole. Whereas magnetic axis is an imaginary line that passes through the magnetic north and the magnetic south.
So do these both axes coincide?
No, they don't. They keep varying from place to place. That is why we have something called as declination or variation. I'll come to that point slowly. Yeah. So it is like a zero error. I'll tell you what it means. So you understood what is axis, right? Axis is one dimensional. In a similar way, across this north pole and the south pole, if I'm able to draw a plane that is cutting through the magnetic north and the magnetic south, then that is called as magnetic meridian. So meridian is a plane, axis is a line. Are these 4 points registered in your mind? Is there any confusion? No, right? No. The important point that you need to note here is the magnetic axis and geographic axis do not coincide. So they do not coincide always. Okay. Okay. Means if suppose you're standing somewhere on this part of the earth, suppose you're standing somewhere on this part of the earth, then what will happen is geographic north and geographic south will be at the same location, but magnetic north and magnetic south will not be at the same location. And what will happen is you can see some variation that is taking place between the magnetic axis and the geographic axis, which is called as magnetic variation, or more technically it is called as magnetic declination. Okay. So it is something like a zero error. Means if you want to reach to a particular location, you need to make a correction in that magnetic declination. Only then you will be able to reach that particular location. We'll do a problem based on it. Then you will understand. Yeah.
So does this mean that the magnetic axis is always fixed while the geographic axis varies with respect to the person, with respect to the position of the person?
Yes, it will vary. Means if you're standing in India in a particular location, it will vary compared to the same person in India in some other location.
So the geographic axis keeps on varying.
No, geographic axis is constant. Magnetic axis will keep changing.
Okay, sir. So magnetic axis is the one that changes.
No, yes, that is the one that changes.
Okay, sir.
Yes. Okay, I'll show you. So first, write down a word called as magnetic declination. Okay. So now what we are going to discuss is components of Earth's magnetic field, or you call it as elements of Earth's magnetic field. Okay. So the first word that we'll see is, whenever you want to do any kind of a calculation, right? You want to reach a particular location, then there are three important parameters that you need to know. One is called as magnetic declination, or you call it as magnetic variation. The next is called as angle of dip or magnetic inclination. And the third one is called as horizontal component of Earth's magnetic field. Just give me a minute. I'm just trying to get a chart and show it to you. See, I'm just sharing my screen. Observe, okay? You asked me, no? Maybe if I show this, you'll understand things better. See, you're able to look at this chart.
Yes, sir. Yes, sir.
So this is something I took. See, you're able to see, find the magnetic declination in India. In India itself, these many places are there. Okay, suppose I click on this. I don't know where it is. You're able to see this value.
Yes,
So
sir.
in this place, it is plus 2.86 degree. Okay. Similarly, I click on something else, plus 2.33 degrees. You're able to understand. So magnetic declination will keep changing from place to place. So you need to know this value to reach the exact location, or else what will happen is you will have an error of 2.73 degrees. That is why if you see, right, sometimes Google Map also what will happen is when you're on the terrace and you're trying to send, you would have sent this WhatsApp location to people, right? You will send current location.
Yes.
Have you ever done that? So next time when you do that, right, when you check it, right, in the current location, it will show approximation of some 65 meter. That is why sometimes when you send it, right, if you send it from the terrace, there is a possibility that you pick the location from next building also. Because all these things are working on the basis of what? Earth's magnetism only, right? That is why your Google Map is also going to work. How is it able to show the navigation? So, are you able to understand? So, if you look at this, there are three terms that I told you, right? Magnet or a place thing. These are all the things. These are the coordinates, latitude and longitude. This is how the coordinates on the Google Map are located. Similarly, you have something called as magnetic declination. So, declination is positive and it is in the east direction. How to solve problem that I'll teach you. Inclination per 53 magnetic inclination. I told you the magnetic dip. That's what you're learning. 53 degrees, 26 minutes. Adhe mari magnetic field strength at this particular location. Look at the value of it. No, it is in terms of nano Tesla, 10 power minus 9 Tesla. So it is that weak. Are you able to understand? So this is how things are calculated and the real world works. Okay. So just wanted to show you. We'll get back to the subject. Okay. Now I think you got a little bit perspective, no? So this is actually a little complicated concept. I don't want to get too much into detail also. That's not a headache. We are not going for a hike tomorrow and we're not concerned about finding the exact location. If you know the theory, that is enough. Okay. So magnetic declination or variation. So what you call magnetic declination as? It is defined as, I told you, right, the magnetic axis and the geographic axis do not coincide. So if you are able to measure the angle between the magnetic axis and the geographic axis, then that angle is called as magnetic declination or variation at that particular location. Is that clear?
Yes.
So it is defined as the angle made by, see, magnetic axis and geographic axis is the same as books mainly try to speak in terms of meridian. Meridian, now you have one plane like this, magnetic plane, magnetic meridian. You have the geographic meridian like this. If you're able to measure the angle between them, you're able to see. So this is the angle. So if you're able to measure this angle, you call it as magnetic declination. Okay. Now next is angle of dip or magnetic inclination. What happens is, listen to this carefully. When you observe the compass, right, I told you compass needle will start experiencing torque. But when it is experiencing torque, right, it will not stably rotate like this. It will rotate like this. You're able to understand? It will rotate in this way. Means it will get dipped. That is what is called as magnetic inclination. So what happens here is, when you take the magnetic field at a particular location, right? If I take this to be the magnetic field, you saw that value, 5.1 something nano Tesla. So this is the direction in which magnetic field is going to exist. Means the compass will get aligned in the direction of magnetic field. Then this angle is called as delta, which we'll call it as angle of dip. Means when this compass needle, instead of being horizontal, right, when it is getting like this, then this magnetic field can be resolved into two components, horizontal component and the vertical component. So the angle made by the magnetic field with the horizontal is what is called as angle of dip. Dip is because it is dipping, right? So it is dipping in the vertical direction. That's why we call it as angle of dip. And this delta is a very, very, very important term. So how do you define angle of dip as? The angle of dip is defined as the angle between the Earth's magnetic field. Earth's magnetic field is represented with the symbol BE, and the horizontal component of Earth's magnetic field. The angle between the Earth's magnetic field and the horizontal component of Earth's magnetic field is what is called as angle of dip.
Yes, sir.
Okay. Now, this B can be resolved into two components, BH and BV. H stands for horizontal, B stands for vertical. Upper BH, I can write it as BE cos delta, and BV, I can write it as BE sin delta. So the third one I told you, right? Third component of Earth's magnetic field, what is it? The horizontal component of Earth's magnetic field, and the horizontal component of Earth's magnetic field is what is BE cos delta. Then what will happen is, if I want to find tan delta will be equal to BV divided by BH. Purida. So
Yes, sir.
sometimes what they will do is they'll give you the vertical component of magnetic field and the horizontal component of magnetic field and ask you to calculate the angle of dip. Then you will do tan delta is equal to BV divided by BH. As simple as that. That's it. Is it clear?
Yes, sir.
Yes. Now we can try out few problems based on this. Just give me a minute. So I'll do only important problems. I'm not doing everything. So these are the terms. Magnetic declination means angle between the geographic meridian and the magnetic meridian. Relation between elements of Earth's magnetic field. BH is equal to B cos delta and BV is equal to B sin delta. BV by BH is equal to tan delta. Another important thing is I can write BE square is equal to BH square plus BV square. Then the Earth's component of magnetic field will be equal to BH square plus BV square. That's it. Okay. These things are not needed. Now, having said this, let's try out a problem. So the declination at a place, I don't know what place it is 15 degrees west of north. So if I take a diagram, north, south, east, west. Okay. So the declination at a place is 15 degrees west of north. Means from north, I have turned towards west through an angle of 15 degrees. In which direction should a ship be steered so that it reaches the place due east? So magnetic declination is 15 degrees, correct? Huh? Where is this person wanting to reach? He wants to reach the east. So how much should be the angle through which he should actually steer? It is 90 plus 15 degrees, which is going to be 105 degrees. Is that clear?
Yes, sir.
Yes, sir.
Right? It's a simple problem. Okay. Next is this. Concentrate on this one. There's a good problem. There is a ship who is intending to reach which point? Who is intending to reach 10 degrees south of west. Means from west, you have turned 10 degrees towards south. In which direction should it be steered? If the declination at the place is 18 degrees west of north. So 18 degrees west of north is, from north, the magnetic declination is 18 degrees. Right. So how much should he steer? Means, actually, I'll tell you what is happening. You know what is happening? He has a compass in his hand, right? And the compass, he is assuming that this is the north direction. But what is happening? This is the magnetic north. So he is assuming that he is actually going in this direction. No, there is an error of 18 degrees. So if he knows what is the error that has occurred at his particular location, then he will know how much he is supposed to balance so that he is able to go in this direction. So how to calculate that? If this is 18 degrees, then this will be 72 degrees. So what will be the total angle here? So from the actual direction in which he is going, he should steer through an angle of 82 degrees so that he will be able to reach the destination which he is desiring to go. Am I clear, guys? Am I clear?
Yes, sir.
Yes. Okay. Next is third one. This you guys can do it. In the magnetic meridian of a certain place, the horizontal component of the Earth's magnetic field is 0.26 Gauss and the angle of dip is 60 degrees. What is the magnetic field of the Earth in this location? So BH is equal to another. BH is equal to B times cos delta, which implies BH, I'll substitute it here, 0.26 is equal to BE into cos 60 degrees. So that will be BE into half is 0.26. Appa B evlo irukum?
0.5.
It is 0.52 Gauss. So the Earth's magnetic field at that particular place is 0.52 Gauss. Okay, generally this is how the values will be. It will be that small. Gauss and 10 power minus 4 Tesla is that small. Okay, this fourth one is not needed. Fifth one will cover all the models that we have discussed. So horizontal and vertical component of Earth's magnetic field at a particular place are 0.22 Gauss and 0.38 Gauss. Calculate the angle of dip. Tan delta BV divided by BH, which is 0.38 divided by 0.22. So you will calculate this value and you can write delta is equal to tan inverse of whatever value you get here. The next is you need the resultant intensity of Earth's magnetic field. So what is the relation between Earth's magnetic field and BH and BV? Root of BH square plus BV square, correct? Is this right?
Yes, sir.
So you know the values, just take them and substitute it. 0.22 square plus 0.38 square. That's it. Okay. So this is all about Earth's magnetism and the overall chapter. So there is one small point that is left out, write down, which is called as Gauss Law of Magnetism, which is just one step. So Gauss Law of Magnetism states something like this. The loop integral of B vector dot dA vector is always 0. Because magnetic field lines always form closed loops. So when magnetic field lines are always forming closed loop, what we can say, the surface integral of B vector dot dA vector is always a 0. Unlike the Gauss law for electrostatics. In Gauss law for electrostatics, it is Q by epsilon naught. Whereas in the case of Gauss law of magnetism, the total flux that is always enclosed by a surface or Gaussian surface is always a 0. That's clear.
Yes, sir.
That
Yes,
is
sir.
all with this chapter. And wait for a minute, don't leave. Yes. So if you check your WhatsApp group, right? If you check your WhatsApp group, I have sent a message which speaks about the test schedule. Okay. So we have written, you wrote only one test till now. That is from electric charges and field, first chapter. But I completed almost, so fifth chapter is also over today. So what I want you to do is, you start preparing on electrostatic potential and capacitance. And did you guys open the message?
Yes, sir.
Yes. So I've given the chapter name, date, day, timing, mark, and note also. So in the second chapter, there is no deletion. In third chapter, potentiometer is deleted. And in the fourth chapter, cyclotron is deleted. Is it clear? So you start preparing accordingly. And one more important update is study materials have come to the institute. Okay. So tomorrow we have a little bit of organizing work. Once that is done, we will drop a message in the group. Then you can come and collect the study materials on Friday. Is that clear?
Yes, sir.
Yes. So that's it. Okay. So that's it from my side, and we can wind up. And yes, I'll be giving you assignments for before the test also. Ensure you're working on that and reach out to me if you have any doubts.
Yes, sir.
Okay. That's it. Can wind up, guys.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Thank you, sir.